Section 5.2, Displaying Sensor Values in Arbus. This section will teach us how to integrate lidar cameras in depth, both in Gazebo and then interpretations in Arbus. Though in this video, we will only cover the lidar section and then encourage you to study on your own how to repeat the process for cameras and depth sensors. So, displaying sensor values works best when Gazebo and Arbus work together. This pair of programs can perform very realistic emulation of common sensors. For example, lidar, which is laser-based or light-based cameras, whether it's one, two, or multiple. Depth sensors like Kinect, actions, and real sense, even force torque sensors. Actually, Arbus is not, and Gazebo are not limited to any particular number of sensors. Any type a new sensor is created, plugins can be created for both Gazebo and Arbus in order to emulate or simulate how those sensors work. Being able to display these sensor values, as we mentioned earlier, can be useful for offline development of sensor-driven behaviors. We can see how the data is behaving, whether we think it's correct or not, and then create some modifications. So in this section, you will learn how to simulate sensors in Gazebo and then how to interpret the information in Arbus. If this is the first time you are being introduced to lidar, lidar stands for light detection and raining. Here's an example, a picture of an example of a lidar result on a street after it has been traversed. I have included YouTube and Yoku video if you want to see a gentle introduction to lidar below. The basics of lidar are as follows. The sensor sends out a light pulse at fixed angles, so it might span a movement from left to right. It might move, say, from negative 90 degrees to positive 90 degrees, spanning a width of 180 degrees, and different light pulses might be sent out every 1 degree for a total of, say, 181 readings. So that light needs to travel there, hit an object, and travel back. We call that the time of flight. And to get the actual distance, we need to divide that time by 2. Then, if we want to extend lidar to 3 dimensions, we would take what are spinning mirrors and move them or rotate them in a vertical and horizontal direction. So this laser is kind of turning on its side, and getting three-dimensional information. You can refer to the book for an example of Atlas, which used a Carnegie Sense head with a spinning mirror. You can also search online for the Carnegie Mellon head to look at 3D lidar measurements, for an example. So once we get the time of flight and we also have the fixed angles, then we can map that information to get an idea of the pose of objects with respect to the reference frame. Now, so all this lidar information in RAWs can be saved into a message type called sensor messages laser scan. We're going to start by using the 2D simulator from before and extending it to include lidar. So we're going to use this lidar CPP file and the lidar alarm package to learn a little bit more about how we can do this. So as we mentioned earlier, the laser scan message type is used for lidar, and you'll see that in this message we have a header where we most importantly have a frame ID attached to that data. So this will be the parent frame of the data, or the sensor frame. We have a minimum and maximum angle or width for the sensor, and also we have that angle increment. What is the spacing across measurements? There's also a time increment depending on the speed of the sensor, and then the time at which a scan takes place, and then some maximum and minimum values for the actual sensor itself in terms of distances. How far and how close can that information be? And then we can get the actual distances and some intensity values from the lidar. Depending on which lidar you're using, this information will change. Remember that if you're using a real robot, then actually what you would have is a hardware node that contains driver code to read the data from the lidar sensor that then would be passed on to this ROS message type. But for simulation, what we need to do is we're interested in working with Gazebo. So the Sacro file, or the URDF file, needs to have, number one, the commands necessary to simulate the sensor. So the lidar, for example, will be like a box. So it needs a size, it needs a mass, it needs an inertia. Then we also need a Gazebo plugin to define how Gazebo should behave. So if I come over here to my website, so let me just search Gazebo plugin. You can do that on Baidu or Bing or Google. You'll come to this tutorial and see that in plugin types, here in the overview, we can have multiple plugins. Now let me see, we have another page, not this one, where we have the ROS plugins. Here they are. So for example, we might have a camera, a multi-camera, a depth camera, Connect sensor, this GPU laser or lidar, laser, block laser, force plugins, and so forth. Okay, so you can look at this page for more information. So let's take a look at how do we actually integrate the lidar into Gazebo. Back in section 4.1, we were using a Sacro file called MOBOT with joint publication. We're going to take that same file and we're going to augment it. What are we going to do? Number one, include the lidar block, the simulation of the sensor. We're going to represent it using a rectangle and define the visual, dynamic, and collision properties. And then we're going to include the Gazebo plugin, and then save that file as MOBOT with lidar.sacro. So let's take a look. Let me open a terminal window here, so I close that. So here we have the Sacro file, and in line 287 we can see that we have added the simulated lidar right here. So we define this as a link name lidar link, Here is the collision section. So it's based on the origin, size 0.2, 0.2, 0.2. For the visual properties, origin is set to zeros. Geometry is the same. Provide a gray color with these values. And then for the inertial properties, we have a mass of 40 kilograms set at that origin, and then with some inertia information. Okay, and the last thing that I want to highlight here is that in order to have correct transformations, the sensor needs to be modeled as a fixed joint. So in the next section that I'll show you briefly, we're going to say we have a joint and it's called lidar joint, and its type is going to be fixed, and this joint will be able to rotate around the y-axis. Okay, and we're going to set that origin slightly different. Now this origin depends on where the actual sensor is in your particular sensor. This is following a I forget the name of the sensor, but it's referred to in the textbook. And so this needs a small translation. The parent link is set to the base link, or this would be the base of the robot if this was the appropriate link. And then the child link is the lidar link. So you can see this right here at the bottom. And so any information, right here, any information that we get from the sensor will be with respect to the base link. Then the second thing we're going to do is insert the Gazebo lidar plugin. You can click on that link for the example. And what the plugin will do is provide sensor specs. For example, the topic name. And we can see this here at the bottom. The frame onto which this is attached. And a name for the sensor. Actually, here we have a couple of names. Sorry, let's take a look. So number one, we start our Gazebo body here. Set the reference to lidar link. We set the sensor type as a GPU ray. Now this GPU, as I highlight here, means that it assumes we are using a graphics card. If you don't have one, then the data that you get back from simulation will not make sense. For some details on how to run this in different ways, go back to the textbook to learn a little bit about OptiRun. So we have this GPU array, and we're going to call this a SICK lidar sensor. Oh, this is the sensor by which we're modeling, a SICK 200, I believe. And here, there's no changes in pose. We don't visualize this plugin. We have an update rate of 40 Hertz. Okay, and then here's some other specs for the scan of the sensor. It's a horizontal scan. We have 181 samples. The resolution is set to 1, a minimum angle of negative 1.57 radians to 1.57 radians. Min and max distances, and the resolution of those distances. So you can see this is all the information that we had back in our laser scan message. This also has Gaussian noise with a small standard deviation to ensure that we don't get just deterministic results every time. And then we need to say what plugin we're using. So here, let me maximize the screen. The plugin is libgazebo-ros gpulaser.so. This shared library should be available from your default ROS Gazebo path. And if you have properly installed Gazebo ROS, then you should be able to work with this plugin easily. And we're providing this plugin name for the shared library. Finally, we choose the scan and then the frame name for the plugin. So if we want to get this started, we will need 7 steps, although they can be automated even in one single launch file. Here we're going to separate them so that you can see the logic behind all of them. Number 1, we'll start Gazebo. We can do that by saying ROS launch, Gazebo ROS as the package, and just provide or call the empty world launch file. Okay, let me do that with you. So maybe let me do this, ROS launch, Gazebo ROS, empty world.launch. If you remember from one of our previous lectures, this will open both the server and the client for Gazebo. You can push that over there to the right and remove this window if you wish. Then steps 2, 3, and 4 are contained in this launch file, but what we want to do first is load the robot model or the URDF file into the parameter server. After we have that, we want to take that robot model and spawn it or launch it into Gazebo. And then one more thing we want to do is start the robot state publisher. So let's just first look at this file before we launch it. So this is in Mobot URDF, Mobot with lidar. Let me maximize this window and open this file. So let's look at how we do that. We're going to convert the Sacro model file and then put it on the parameter server. So here we want to have this parameter with name robot description that you recall me mentioning at the beginning of the lecture. And then we're going to have a script sacropy. Now this full path can be obtained by calling find on this ROS package name. For example, if I were to do ROS CD sacro, this would return this path name. So when we have the money sign and the parentheses, the value of find sacro will be replaced in this section right here, so we would get the full path. So as you can see, we have the script right here, so this is basically like calling sacro.py on a file. And so how do we do this? Here we have find again. We're looking at Mobot URDF inside the URDF folder and then using this sacro file. So if I really wanted to do this, I could kind of do this for me, learning ROS, Mobot URDF, Mobot with lidar.sacro. And when I run this sacro.py on this sacro file, I'm going to get the URDF, which should be a fairly long file. So all of this that you see right here in my window then would be saved into this parameter robot description. Okay? That's a little bit of how you can understand a launch file command in a terminal. Then the next thing that we want to do is use the Gazebo ROS package and the spawn model node and take this URDF or robot description parameter and load it onto Gazebo. So the key part is in the arguments. Here we're going to say for we want to use a parameter, not a URDF file. We're going to use the parameter called robot description, and then we're going to have a file of type URDF, and then within that file I want to use the robot called Mobot. So that URDF file somewhere around here will have the Mobot name right here. The robot name is Mobot, and what we want to do then is spawn that or put that into Gazebo. And so when I launch the file, you'll see how this works. And finally, just start the robot state publisher. Okay, so let me close this and then do a ROS launch on this. And bring this to this side and just keep Gazebo on that side. Okay, so as soon as I do that, the Mobot will appear, and let me do that. So I'm zoomed out and our Mobot is right there. So you can see that this launch file started the robot state publisher as well as called the spawn URDF, which has now finished cleanly. The next thing we want to do to make this more interesting is insert interesting world around the Mobot. So the way we can do that is we go to Gazebo, we click on this insert menu, and then we can look for starting pen. Now these models have been downloaded from a Gazebo database. If you don't see them right here, you can contact me for help or look back at the instructions from previous sections to learn how to download those worlds. So as I go back here to Gazebo, I click insert, I go back to S, I look for starting pen, I click on it, and immediately it'll appear and it'll allow me to move it anywhere on the world. So I might choose a location that allows the robot to be centered around a room. And since we have loaded the Cycler file, which includes the Gazebo plugin, this should be currently running. So if I now come over here and say ROS topic list, you could see that the scan topic that we defined in the Cycler file is located right here. So what we want to do now is to visualize this topic in our viz. Okay, we'll see that the values will range, as we saw in our specifications, from -90 to 90 for every 1 degree. So what we're gonna do now is open our viz and set the fixed frame to odometry. Okay, then we will add a laser scan display and select the scan topic as the topic. After that, we will see the markers for the data. But here we'll have a choice to change the style of those markers. So to make them look better, we'll select the style to be spheres. We'll make them bigger and change their size to 0.1 meters. And then we will vary their color according to the distance along a specific axis. So we can select axis color here and then select the x-axis to be the axis by which they vary. You could change this to x or y. The z-axis wouldn't make much sense because all of these points lie at the same z-axis height. So let's go back to our window, and I can open Arbus. Here we can activate robot model. The robot doesn't yet show properly because my fixed frame is incorrect. So if I can select autumn, I'm going to be able to see my robot properly. Okay, then the next thing I want to do is add laser scan. And when I open laser scan, I can choose the right topic. Okay, the next thing I need to do is change the marker size. And you can see that the markers have now appeared in this direction, or in this location, I should say. And here the color transformer right now is set to intensity or flat, or here is axis color. Here we can have change in X, change in Y, change in Z. Actually, there is a slight change in C axis height. I didn't expect that, but basically here what this will mean is the red color is furthest back, and then as you go forward you go into orange and yellow and green and blue and violet, following the rainbow sequence of colors. And so you can see that this is very similar. Oops, what did I do? This is very similar in color to, similar in shape, I apologize, to the wall that we have over here. And so the key thing for us to see here is that Arbus can display sensor data through the display menus and specific topics. Right now we just have the lidar sensor, but the rest of the chapter talks about how to integrate cameras and depth sensors. So as you build your Arbus configuration, sometimes you don't want to start from scratch. You want to keep the same configuration that you have been designing over time for your particular robot. And as you can see, this can grow in complexity. If you want to save it, Arbus gives you the ability to do that. So make sure you click on Arbus, go to File, and then you can save it as save config. Save config as. And here you could maybe go to your ROS workspace and find the right package, and you could create a folder called Arbus. In this case, the book called it Arbus config, and then you could type a particular name for us, test Arbus, although that would be a poor name. A better name would be this one, Mobot with lidar.arbus. And then next time you can simply load this particular configuration of your Arbus file and save you some work. If you want to look at this file, it looks quite complicated. But basically it's saving all the configurations of Arbus into this file and then reading them out again. It's a long file. And as we've been mentioning, oh, and I should say, teach you how to load this configuration. I apologize. So, for example, let me kill Arbus here. If you are in the, oh, we have a launch file. let me see, raw CD, Mobot, URDF launch files. If we look at this Mobot with lidar and Arbus launch file, we see how we can load our Arbus configuration compared to before. We have one last entry where we say, I want to run my package Arbus, my node Arbus. I'll just give a name Arbus to the node. And in arguments, the -d argument is to provide a path to Arbus. So then you can use the find command inside the money sign and the parentheses to get the package, followed by, you know, the relative path, here the folder, and then the file. And by doing this, you can quickly then run the robot. Arbus.launch. Although in this case we have already spawned, but this will just open Arbus with a particular configuration. Now this configuration is not the one I showed you, but it's the one that was saved by the book. So it has a slightly different configuration. This would be mine. Okay. And the last part of this is that we can visualize information, visualization information from Arbus can be used to evaluate robot behavior. So right now we might be interested in moving the Mobot in a circle and then see how the lidar sensor information is behaving. Here we can command the robot. We can publish information to command velocity, this one right here. That is a standard topic for mobile robots in ROS. And this topic is typically a geometry messages twist message type. And this twist message has several components, but one of them is this linear velocity in the XYZ and angular velocity in the XYZ. So we can publish this information at a rate of 2 hertz per second and then see how the robot moves. Basically, you would see the robot moving in circles and publishing or seeing the lidar data change. So let me first open a window here. So we would say ROS topic pub at a rate of 2, print to command velocity. This is going to be geometry messages twist, and then we have these quotes and these parentheses. Then we have the linear part, and we can say x is equal to 0.5. Actually, if you don't have information for y and z, you can leave it open, and then you can say angular. And then here we can set z equal to 0.2. Now let me open this one, and I should in fact open Arbus again to display the robot. Actually, let me just launch the launch file I had before to quickly open Arbus. Okay, and let me change the intensity to axis color along the X direction, so you should feel very familiar with this by now. I can zoom in and let me maximize this window and then bring it down here. So when I press enter, if I didn't type anything wrong, you'll see that my robot is moving in circles, and that the data in Arbus is being updated as this robot moves. Now the cool thing about Arbus is that you can rotate the world and see it from different angles. Even though you know, Gazebo might just be pointing in one direction. Okay, and you can zoom in or zoom out. You can pan or you can rotate around that world to see if what's happening in the world agrees with the data that you're seeing in Arbus. So this is why we say it's useful for debugging, because it helps you to make sense of data according to the environment you experience in the